Yeah, the main purpose of Unit 2 is I would like to actually predict from which part of the DNA actually codes for the gene trait. Once assuming I have the DNA sequence. Where to get the DNA sequence? In this example, from GenBank. So let's get started. Let me try to make it. Why don't we do the hands-on? Okay. But before do that, I need some brief introduction. For the prokaryotic gene structure, it's polycistronic, meaning that one long mRNA molecule may code for multiple proteins with single promoter, which is very different from eukaryote. Typically in eukaryote, one promoter immediately followed by the coding sequence of a gene. That is a unit, the mRNA. So one mRNA code for the one gene, but in the bacteria, one mRNA code for multiple genes, what we call the operand, or here is the one example of that. The coding sequence here code for one gene, ULA gene, separated by one or two nucleotide right after the stop codon, followed by the start codon of the next gene, and second gene, and immediately followed by the third gene, fourth, like that, separated by one or two or not so many nucleotides. So this is very unique in the prokaryote. And also many prokaryotic genes the mRNAs or those genes, DNAs are circular. Some are linear, but there are many circular molecules, so be aware of that too. So now I would like to mention about the RNA-seq. RNA-seq, if you use the NGS, next generation sequencing, and if you sequence RNAs, we sequence actually cDNA, complementary DNA, because the sequencer that we typically use can sequence the DNA, not the RNA. But cDNA contains the same information as mRNA. So RNA-seq is basically you are sequencing the mRNA molecule, and then if you sequence that, it gives not only the gene expression, how much it has, how many copies of mRNA molecules, which is what I mean by the gene expression, but also it contains the information of transcription start and stop site, so you can identify where it is in the genome. And so gene predictor, the computational algorithm, is pretty good at finding the coding sequence of start site and ending site, but not good at the mRNA locations, which is complicated because of this the changing start site to the processing it and caching and those kind of things. But however, RNA-seq is very good at finding the mRNA locations, but not really good at the coding sequence locations. So in reality, we use the both for not only the gene predictor, but the RNA-seq. Here is one of like a pipeline that we use the example of that to accurately annotate the gene structure in that unknown sequence. Now, what is the open reading frame? Is there anyone who want to volunteer to answer? Yeah.
It's the sequence which codes for the protein, like the start and stop. So that's one protein.
let's say in analogy, let's say that start codon ATG, start the that coding part, and then stop codon close it. So it's basically open reading, right? And then so I'd like to get some volunteer to share your screen and actually go over this example. Is there anyone who want to volunteer? Feel free to volunteer. I'm going to stop my screen sharing. Oh, I didn't share the screen. Sorry for that. Yeah, I'm doing the recording, so what I meant is I wanted to share the screen. Yes. Thank you. Yeah, this is the Open Reading Frame Finder. Thank you for sharing it. Aritra, thank you. Now, you want to paste the sequence in FASTA format. Do you have any tab open for Genome? Who's the yeah. So can you click the FASTA? Can you click the send to go up? Go up. Can you go up? Yeah, send to. Yeah. Click it. Can you click the file? Download. Create the file. That's good. So in this way, you actually download the sequence to the file. You have to drag Control V to copy, Control V to paste. It's okay. You can do that, but now can you go back to the ORS Finder? Can you paste either copy and paste or upload is not available? Yeah, sorry for that. Yeah, let's just do the copy and paste. You can open with the Notepad or WordPad, Control A to select all, and Control C to copy, and Control V to paste here. Thank you. And go down. And then click submit. So you are using Open Reading Frame Finder, and here is the Open Reading Frames in that long stretch of reading. So it's not required to find the Open Reading Frames, right? And then this is a graphical summary. Good. And then can you go down? Yeah, here are the some specific technical details from where to where. There is an Open Reading Frame. Open Reading Frames exist in the forward version, which is the Genome plus, or the other version minus. Right? Thank you for sharing it. And any question about the Open Reading Frame Finder?
If it's minus,
Yeah.
if it's minus, does it mean it's like in the bottom strap?
Pardon?
If it's in minus reverse directions, that means it's from 3' to 5'.
That's right. That's right. That's what it means. Right. So this software tries to find the longest the open reading frames and not to overlap each other to the real genes. So open reading finder, you already know what's going on. And what about let's try to use FGeneSB, the bacterial operon and gene prediction software. This is previously you just identify the start codon and the start codon and the possible open reading frames. But this time we would like to add on some more information so that we actually want to find out some candidate genes using another software called FGeneSB. Now, and would you please the volunteer? I'm going to stop share and click this link, and then yeah. And is there anyone who want to volunteer for this software? Thank you for sharing it. Robisha? Who is okay, thank you. Can you click the PowerPoint slide? Yeah, good. And did you come to this? All right, good. Can you copy and paste the FASTA here? That go to the Genbank?
The same sequence.
Yeah, any sequence that you already got, and drag it to highlight, Command C to copy, and Command V here. Thank you. And click process. So you can change the archaea generic or bacteria generic depending on whether you are studying archaea or the bacteria. If this is a bacterial sequence and you want to use the bacteria generic, then this is just a proof of concept. So for that purpose, it doesn't matter.
Still loading.
Okay. Good. All right. So you are looking at the gene prediction. Start codon location. First transcription unit. Start with the 202 to the 1557. Are you familiar with this number, right? It's actually correctly predicted. But I want you to be critical, right? Because gene prediction is not 100% correct all the time. Anyway, it predicted the first coding sequence 3DS in the plus direction. The first transcript unit is from there to there. And then first operand unit is from 1709 to the 2800. The 45 with the following score. The second mRNA molecule has another gene, which is denoted by operand 2. It's starting from 2920 to the 3117. So let me write it down here. So I want you to focus on the second and third line. The second and third line. Can you highlight the second and third line? Yeah, that one. Good. Do you see that transcription unit T is the one transcription unit, meaning that one mRNA molecule, it has two genes. operand 1 and operand 2. So in this long, like a transcription unit, or mRNA, it has the first operand is starts with the 1700 lines all the way to 2845. Okay. So this is the one operand unit, and another operand unit is 2920 to the 3017, right? Okay. And where is the start codon? Start codon is 1709 to 1711. 9 and 11, 3 days there in HG. Start codon location is 2843 to 2845. Those 3 days. Okay. And then there's some gap, and then followed by this. And this gene is located in the clusters. But here, when you come down, there's some negative direction. For that case, can you highlight this line? This is one transcription unit, one gene for the one gene for one mRNA, and it's located in the negative direction. So start codon location is located not here but here, 20031 to 20029, and then stop codon location is located to the starting from 19879. 85 to the 82. You understand all of the detail? Okay, question?
Sorry, grouping the operands into one transcription unit. Is it based on the number to the left? Is it 2 OP? Like, is that what you said?
How do you see that? Yeah, do you see that? It has only one gene for each transcription unit, which is mRNA. So one mRNA. For this, it has the 3 operands. So it's organized that way.
So one operon is one protein.
For this, one protein, but for this operand, 3 proteins in one.
So it's pairs and over the next is the conserved pairs. Well, does that mean that this is just being out on the
yeah, the score is how confident it is.
and then the conserved pairs.
The conserved pairs, where is it?
Right, like the one before the
anyway, some meaning.
okay,
This
this
is
is
just
Can you explain the negative, how the start and stop codon is for the negative?
the negative direction. So DNA we usually read from 5' and the 6' right? So start codon is located near the 5' end position, and then stop codon is located in the 3' end position, right? But that's only when the gene is in the plus direction. When the gene is in the negative direction, we reverse it. So start codon is not located nearby 1982, but located by here. But start codon is always 3 base pair long. So start position of that start codon is 20031 and 20030 and 20029. And when you have the DNA sequence, it's probably within complementary. So you have to the reverse complementary. Yeah.
Sorry, one question. So you said transcript gene is okay. So on the top it says it has 1124 transcription units and 418 operands. Does that mean a lot of them are non-coded?
Yeah,
a lot of them are just what is that?
one transcript unit, and then it's not multiple,
What is it?
so in a lot of cases are like this. No operands. In this case, three operands compose the one transcript unit, but a lot of them are just one gene and one like a mRNA.
And what does the score indicate?
Score indicate the confidence, how much you can trust these predictions. Higher, more likely.
Is there any like limit?
Cutoff? It's very subjective. Yeah. Yeah. Question.
So why are two there before operon? Like there are two operon and two operon again, and three OP, three OP.
Yeah. Can you highlight two lines here? Okay.
Oh, that is 2 out of 2, and then 3.
Okay. This is second transcriptional unit in the genome structure. So mRNA, like that, and it has two genes in it, operon 1 and operon 2. That's what she's highlighting. Did you explain or?
So does it mean they correspond to the first one TU? The first one TU. So the two OP correspond to the first one TU. Or
No.
is it like a individual entity? I did not get where this program is present.
All right.
TU is a transcription unit.
T is a transcription unit when there is only one gene in it. When multiple genes in it, they call operands. That's why it T or OP. The transcript unit or the operands. Yeah, this is their kind of notation. In the computation, we have to get familiar with their notation. Good. Yeah.
How do those numbers signify which are on the left and right of the opening and 15
Yeah. Again.
The numbers which are on the left hand side and on the right hand side of the opening, like 2, 1, and 2, what does this signify?
2, 1, 2, 2. Which number?
Like in the TU column, there are two numbers on the left and right.
Highlight me. I tried to.
Which second one column?
I think you're asking the numbers like on the two sides of OP and TU.
Oh, 2 OP1.
Yeah, so
The numbers.
What is 2 and 1? What does it signify?
One
Do you
transcription.
get that operon 1 and operon 2? That's what it means. Let me explain the right side first. This is operon 1 and this is operon 2. Right? That's what OP1 and OP2. But both has the 2, right? And this is
The 2.
the second transcript unit. That's what
Signifies the transcript number.
Yeah. This column, the second column tells you mRNA molecule. And then third and fourth column basically tells you the DNA.
Yeah.
Now, thank you for the sharing this. So now you have done the gene prediction using this software, which is not that hard, right?
I have another question. Are the results from this website will be the same that we see in the gene bank? I mean the numbers like 202 to 1557, and they are will all match it to the gene bank.
Okay, that's a very good question.
Yeah, because I think
prediction. be the same as GenBank substitute?
Not really.
I hope so, but
Oh, okay. So might be a
yeah,
little difference. Oh, okay.
and how to validate by doing RNA-seq or some complementary experiment.
But we are copying the master sequence from gene bank only, right?
Yes, so you have to actually read the paper.
Oh,
The check. How did they just use the gene prediction? Then their annotation can be wrong. If they validate in the paper, hey, we use this method, then we actually check it, then it's likely to be correct. So, so now the situation is when you are given a new sequence, what to do? Yeah, why don't you try this software?
Then compare a little bit.
Yeah. And I just open reading frame is open reading frame. So just a possibility of the gene, right? But this software actually predicts gene. But I told you that gene prediction can be wrong, right? So why don't I introduce another software? So you can check out whether these two software predict the same way or different. Okay?
So whatever we got, that is called annotation.
Yeah, you just get the annotation using one software. But we are not 100% sure. So let me introduce another software so that at least I hope the consensus of these two software is correct. And if we know the answer, I probably introduce only that software. Hey, just you use this. But even ChatGPT it hallucinates, right? Yeah, so there is no perfect computation algorithm. That's why I would like to introduce another software for you, which is Believer. Now, yeah, I would like to give some challenge. So far, I appreciate your participation and those who share the screen. But this time, it's going to be slightly challenging because we are going to use the command line. Okay. I would like to get the volunteer who use a Mac. Mac. And then which one is better? Who knows the command line better or who will not have a much experience? Anyway, I will let you decide. Can you share your screen? So let's try this demo together. And it's actually your own benefit because let me repeat this. This will be integrated homework, and you know what it means. So is there anyone volunteer? So we will troubleshoot together for those who want. Thank you. Hi, Jen. Thank you for the volunteering. And did you log in? Can you do the LS? This is your own computer, right? Yeah. Can you log into the BFX3 server? Everyone knows how to log into getting into the BFX3 server, right? Please do it together. So are you there? Yeah. Can you do the LS? Yeah, that's good. Now. Just one moment. I want you to get the FASTA sequence here. from your own computer to here. So that's what I want to do together. So let's start with the JPEG. Can you go to the JPEG? And then just choose anyone you want. Yeah, but can you click the send to?
I will click down.
All right. And can you, where is it? Yeah. And just one note. When you download again and again, it often has a parentheses. Right? In the Linux, I want you to avoid that kind of thing. Delete. So just prepare that kind of simple, like a sequence that press A like that. Sequence. If you happen to have this sequence, that's fine. Open parentheses and close parentheses. If you want to use this in the Linux, you have to add a backslash, which is complicated. So what I suggest is just prepare sequence.passport without any space in between. Okay. So I think a Kaizen is ready. Then how to upload this to the BFX3 server? CP is a copy command. You can copy from within one system. But now you are talking about copying from your computer to the server. It's an SDP command or file or min SDP. So let me introduce the software. You have three methods. You use the SDP command. This is one method. The second method is you use the file for Mac people. Or if you are Windows people, you can either use FileZilla or you can use the WinSCP. And then which those unless you are really big fan of command line, I recommend you to use either FileZilla or WinSCP. So yeah, FileZilla please. Do you have the software installed or not? Yeah, let's install this. FileZilla client. You are using it as a client. So client is the right one. Can you install that? Yeah, download. And then when you download it, install this. So I recommend you to start with the FileZilla. For the host name is the IP address. bfx3.aap.jhu.edu. And username is your Johns Hopkins ID. And password is your Johns Hopkins password. Port is 22. Yeah, you don't have to say it's your choice first. Are you sure to connect? Okay. Now you connect it to the server. Right? The right side is the remote server, and then left side is your computer. So, can you find the sequence.fs file from left and then drag to right? Sequence.fs file. You didn't download it here? Do you want to download it again to the desktop? While he's speaking, yeah, I want you to do the same thing. Can you install the FileZilla? And then did you connect? And you know how to download the FAFSA file right to your computer? And can you drag it to the right side so that you can upload to the server?
Drag it anywhere.
Yeah.
That's this one.
Yeah, you did it. But you go to the command line, and when you do the ls, do you see the sequence
I think it's not really.
Oh, there is a sequence of FAFSA there. It's not failure, but let's check out the content of it by the last command. LESS space and then the sequence of FAFSA. Okay, so good. So you correctly imported and you can print by pressing choose. Good. Now you're ready to use the gene annotation software. Right? Can you copy the first command? Yeah, and then paste it here, but don't run it yet. Where is that? Oh, you already run it. Okay, let's just copy it. Then why don't we actually type together? Yeah, type together. Let me give the some. For you, I'm going to provide my computer so that you can. Yeah. Oh, yeah.
这个是用
Okay.
用它那个
After
PPT 开
dragging,
始的。
what do we have to do?
After dragging, when you drag it, the computer. Can you log into the remote computer via this command line? And then ls. Yeah, enter.
哦，这个要打20。
Do you see that the sequence of FAFSA is there? How do you get it? Did you already download it? The download folder, there should be sequence of
超
FAFSA.
紧凑的。
Yeah, try to find it and just drag it. Oh, but you're but you are not connected to the Johns Hopkins ID and no. And then port number 22. Yeah, connected. Good. You just drag that file here. Okay. Any questions so far? Are you ready to type that? The first thing that I would like to do is when you do the ls here, ls list, can you make it somewhat up?
Can you just send that in?
Yeah, ls, you should see the sequence of FAFSA. That's one thing before we start. Right? Yeah. So when you do the ls command, you should be able to see the sequence of FAFSA file. That's kind of really good. Right? Okay. Yeah, let's get started. The first step is trying to make a long open frame from sequence of FAFSA. So the command is can you type LBG? It's not, yeah, I cannot really see that. Yeah, that's the command. Yeah. Long open reading frame minus n minus t 1.15. You can read what are these from the reading material. And then you provide your sequencer FASTA. Out of this, you want to create sequencer long open reading frames. So sequencer FASTA is your input file. Based on that, you want to generate open reading frame of it. Just the same way as we use the open reading frame finder. So before you use the Gleamer for gene position, we want to get started with open reading frame because those are candidates of the potential genes. So now, yep. Can you actually this here? Yeah, I cannot really see the bottom here, but did you pass? Can you make a screen smaller so that I can see the bottom? Yeah, good. Thank you. The second command is, can you copy and paste that? Yeah, you want to extract from your FASTA file, which is the sequence.fasta. And also, you want to provide the long open reading frames that you made. And then you want to generate the sequence.train. You want to get the training based on that. Yeah. Now you have the file. You are done with the training. Once you have done the training, it's the next step. Can you copy the next command? You want to build the model. Yeah. You want to build a model in the reverse way. Can you use the up arrow key again? Up arrow key. Can you come to here, this minus sign? And I want you to, this minus and this minus, show this minus is somewhat longer. I don't want that. So can you delete that and retype it? No, build IC, yeah, that's right. Space minus R. So this R is minus, is a somewhat shorter, which is a regular one. When you do the copy and paste, yeah, yes, so I made the error. Yeah. Enter key. So based on that training, you are making the model. That's what you have done. So now you have that model, ICM, integrated model.
So what does the second command do?
Second command is trying to train on the open reading frame. The third command is doing making a model based on the
train in the sense, what does it do?
Pardon?
Like
Train on the sequence pattern.
Like they did.
Yeah. Like Promoter has a certain pattern, right? That's the basic train. Right? Okay. Now let's move on to the final command, Glimmer command. Yeah, for the minus, be careful because when you copy and paste, the minus is encoded different way. So I recommend you to retype the minus. That's what the typing is doing. And you provide the FASTA file and then the model file, ICM, and then you also provide you provide a new name for it, and now you're ready to run it. done. Can you do LS? Now you produce the sequence glimmer.detail and sequence delay glimmer.predict. That file was what I was looking for. I asked you to predict gene structure based on the FASTA file, but by doing this, first try to find the open reading frame, second training, third build the model, then use the glimmer to do that. Yeah, by the last, can you run it? Those are the genes that glimmer predict.
After extract, like we have to type the last command,
Pardon?
the extract.
Okay, we will go over that.
So this can come like only this case. Like after I did glimmer, this came.
Yeah, it's done. So you have a predict file. Sequence the predict file. And do the less on sequence the predict. If you run less on the sequence the predict file, you will see that.
So just keep it all like that.
Yeah.
So when I put the big one,
Pardon?
like commercial, there's a strong commercial.
Did you do the retype the minus sign? We delete that. Yeah, and then yeah. Okay. Let's try to run the final extract minus CD. You already have the prediction, but based on the prediction, let's generate the some other information.
What I can see the sequences
Good.
So
That's fine. Can you do the less on that? Less on that. It should be less. No, I want to check out the result. So can you delete everything in front of it? Less of the sequence glimmer.glimmer. Glimmer.glimmer. Yeah. So even though it has error, it produced. Previously, it just took the location. Now we have a sequence image.
but how to get back? Like so, if this came, how to get back?
Yeah, Q for quit from the last. Yeah. Can you show the last command? Q to quit. And the last command is the extract. Yeah, that one. So let me summarize the steps. The big picture first. We wanna predict gene structure of a prokaryote. And previously you used the website, but called the other software. But why don't we use the new software called the Lunar? And first step is the use long open reading frames command. You generate the long open reading frames. And can you highlight the extract command? Yeah, thank you. In this command, extract, you basically want to extract from using the FASTA and open reading frame information to get the input that will be used for training. And then can you highlight the number 3, the next line? You want to build a model
Or you can't do that.
based on the training data you generated in the previous step. Can you highlight the glimmer? You want to use a glimmer tree with some parameter set here, so that you get the glimmer out. However, glimmer out would just provide the location, not the sequence. So I would like to integrate the sequence with the location. That's the final step, extract step. Yeah, even though it has error, it should work.
Oh, it should.
Yeah, can you do the last comment?
That's the lower part.
Yeah,
We can see stuff.
yeah, that's right. Somehow it is, yeah.
Okay, yeah. It takes what?
To delete the previous.
Sequence the predicate is not properly generated. Okay. Yeah, I will go over that. All right. So basically, that is the end of today's lecture. And I will stay here until you guys are done with. So if you want to have a question, I can answer one by one. But I don't want to hold you so that you stay later than the 9:30. 9:30 is the time to plan me. Oh, 45.
45.
Oh, I thought 9:30. Yeah. All right. Now, why don't we actually spend the time? I will troubleshoot. Or I will answer any question that you might have. And if you are done, feel free to leave. Otherwise, I will be either troubleshoot or answer your question.
What does last command do?
Last command does the integrate the sequence information to the location information. Previously, just the gene location information, but you want to add on the sequence information. Yeah, question.
Does both Unit 1 and Unit 2 discussion has the soft deadline on Friday and the hard due on Monday?
Yeah.
I didn't hear that.
Does the Unit 1 and the Unit 2 discussions due on Friday and Monday?
Yeah. We covered like units for this week only. Yeah, and total 6
Thank you.
Yeah, let me stop the recording.
Class